In the world of making computer chips, there is one machine so complicated, so impossibly precise, that only one company on Earth knows how to build it. That company is ASML, and their machine uses extreme ultraviolet light to print microscopic circuits onto silicon wafers. For years, China was told it could never have this machine. The technology was restricted, completely locked away. But China just built what ASML feared most, a working prototype of its very own EUV lithography machine. Instead of buying it, they decided to build it from scratch. And they did it by taking a completely different path. The machine is so massive that it reportedly occupies an entire factory floor, while ASML's machine fits in a space about the size of a school bus. Why is the Chinese version so huge? How did they build it without the critical parts they were banned from buying? It is a story of exploding metal, mirrors so smooth they put telescopes to shame, a hidden gas that you find in party balloons, and a secret hiding inside the minds of engineers. If you are enjoying videos like this, please hit the like button because it takes a lot of effort to make these, and subscribe so you do not miss the next one. What you are about to hear is a true story about how a country rebuilt the most advanced machine on the planet, piece by piece. The answer involves engineering choices that surprise even the experts. To understand how China built this giant machine, we first have to look at the hardest part of the whole process, creating the light. The light source problem. Every EUV lithography machine is basically a giant, incredibly fancy printer. But instead of spraying ink onto paper, it prints tiny circuits onto silicon wafers. The smaller you want those circuits to be, the shorter the wavelength of light you need. Modern chips need light with a wavelength of just 13.5 nanometers. You cannot buy a laser that produces this light. You have to build a system that creates it from scratch. ASML's solution is brilliant and a little crazy. Every single second, their machine drops 50,000 microscopic droplets of tin into a vacuum chamber. A small laser hits each droplet, flattening it into a tiny disc. Right after that, a massive CO2 laser hits the exact same droplet. The tin instantly turns into plasma, hitting temperatures around 200,000 degrees Celsius. As it cools, it gives off 13.5 nanometer EUV light. To make this work, the machine has to hit 50,000 tiny moving targets every second, never missing a single shot. ASML spent decades perfecting this. When China decided to build its own machine, they had a choice. They could try to copy ASML's exact method, or they could try something else. Public reports suggest China is actually trying both. But the one that stands out is a method ASML abandoned years ago. It is called Laser-Induced Discharge Plasma, or LDP. Instead of chasing 50,000 flying tin droplets every second, the LDP method uses two metal discs that rotate slowly. These discs sit in a bath of heated liquid tin. As they spin, they pick up a coating of tin. These discs act as electrodes connected to huge banks of capacitors that are fully charged. A small laser fires at one of the discs, acting as a trigger. It vaporizes a tiny bit of tin, creating a cloud of tin vapor hanging between the two discs. Then, the capacitors dump all their stored energy. A huge electrical current jumps straight through that cloud. The current creates a magnetic field that crushes the vapor into a hot, dense plasma. We are talking hundreds of thousands of degrees. And that plasma emits the exact same 13.5 nanometer EUV light. It creates the same light, but with completely different engineering. There is no giant CO2 laser. There is no need to hit 50,000 moving droplets every second. It is mechanically simpler and potentially much more efficient. So why didn't ASML build it this way? 20 years ago, they actually tried. The problem wasn't creating the EUV light. The problem was creating enough of it. Chip factories need hundreds of watts of stable EUV power. Without high power, every silicon wafer takes way too long to print. It is like trying to cook a turkey using the heat from a single light bulb. You might eventually get there, but no factory can afford to wait that long. The LDP method hit a physics wall. When engineers added more energy, the plasma got larger, but it didn't get brighter. The mirrors couldn't collect most of it, so they kept adding power without getting more usable light. ASML gave up because, at the time, it couldn't be scaled up for manufacturing. The LDP method topped out at 30 watts, while ASML's newer methods reach over 700 watts. China isn't betting that the LDP method is smarter than what ASML chose. China is betting that today is not 20 years ago. They have better materials and better control systems now. They have demonstrated working prototypes of both methods, though the power is still below what is needed for mass production. But for the first time, they have built their own EUV light source from scratch. Generating the light was a massive hurdle, but surprisingly, the light was just step one. Once you create that light, you have to focus it perfectly onto a tiny silicon wafer. That leads to the next huge problem: the mirror maze. Now you have a source of EUV light, but you have a new problem. You need to focus that light to print the tiny circuits. Normally you would use glass lenses, like in a camera or a microscope, but EUV light is so weird that glass doesn't bend it. Glass just swallows it. At 13.5 nanometers, almost every material simply absorbs the light. Engineers had to rethink the entire optical system. Instead of lenses, they use a chain of mirrors that bounce the light all the way down to the silicon wafer. But these are not ordinary mirrors you hang on a wall. Each mirror is built from dozens of atomically thin layers of materials like molybdenum and silicon. The light has to bounce off many mirrors, and every single reflection loses at least 30% of the light. By the time the beam reaches the wafer, only a tiny fraction of the original light remains. This means there is almost no room for error. Every mirror has to be atomically smooth. Building them is incredibly hard. Measuring and aligning them is even harder. For decades, there was only one place on Earth that knew how to build mirrors like this. It was a company called Zeiss. They didn't just invent one thing. They spent more than 30 years perfecting every single step, from polishing and coating to measuring and aligning mirrors with atomic precision. That is the difference between making a regular mirror and making an EUV mirror. So how did China recreate 30 years of optical knowledge without Zeiss? They broke the problem into smaller pieces. One of the most important groups was the Changchun Optics Institute. They focused entirely on precision optics. Building an EUV mirror is unlike building almost anything else. The surface has to be smooth to around 50 picometers. That is less than the width of a single atom. China already had experience building world-class optics for space telescopes, but EUV mirrors are a completely different story. This level of polish on a curved surface is Zeiss's secret sauce. And even if you can polish the mirror, you have to verify it. That requires measurement tools that barely exist outside of Zeiss. On top of that, inside a running EUV machine, the mirrors are constantly hit by hot tin plasma debris and intense radiation. Keeping those delicate coatings stable for years inside a busy factory is a massive challenge. Public reports suggest that Chinese institutes have already built domestic EUV mirrors and integrated them into prototype systems. Matching Zeiss is still a huge challenge, especially in how long the mirrors last under heavy use. But China appears to be making a very specific engineering trade-off. If your mirrors are less efficient and your light source is dimmer, how do you compensate? You do it with scale. You use larger collectors. You use bigger mirrors. You use a longer optical path. It is the engineering equivalent of saying, if you can't make it perfect, make it bigger. This explains why China's prototype reportedly occupies an entire factory floor. ASML's scanner is roughly the size of a school bus, packed with intense precision. China's version is spreading out, using size to make up for a lack of absolute perfection. The Changchun Optics Institute has reportedly integrated these domestic optical systems into the prototype scanner. This doesn't mean they have matched Zeiss quality. Overall optical performance is still well below commercial scanners, but it is a massive milestone. For the first time, China has assembled a domestic optical system that can actually operate inside an EUV scanner. They solved the light and they solved the mirrors. But the next bottleneck is something you can't polish or engineer away. It is one of the lightest elements in the universe, and without it, the whole machine stops. The invisible gas barrier. Even if you solve the light and build the mirrors, the machine still cannot run without a material that seems incredibly simple. It is helium, the exact same gas that fills party balloons. And yet, one of the most complex machines humanity has ever built cannot function without it. Helium is essential in EUV tools and chip manufacturing because there is nothing else that can do all of its jobs at once. The process of printing chips generates a huge amount of heat, and helium is incredibly good at carrying heat away from the hottest parts of the machine. It is also completely unreactive, meaning it won't damage delicate optics or contaminate the silicon wafers. On top of that, its atoms are so incredibly small that engineers use it to find tiny leaks in the vacuum chambers. If you try to replace helium, chip production stops completely. And EUV machines don't just use a little bit of helium, they consume massive amounts of it. A single advanced chip factory can require 5,000 to 20,000 cubic meters of helium every single month. There is no practical substitute. This creates a massive problem for China. Right now, China imports about 85% of its helium. Its domestic production is under 900 tons a year, while its imports exceed 4,900 tons. Historically, most of that supply came from just two countries, Qatar and Russia. Recently, both of those supply chains came under pressure. The problem with helium is that, unlike oil, it cannot sit in a storage tank forever. It is transported as a super cold liquid, and it is very time sensitive. Think of it like trying to ship a block of ice across a desert. If shipping is delayed, the liquid helium slowly boils away. Once it escapes into the atmosphere, it is gone forever, floating up into space. Meanwhile, the world's largest helium reserves sit in the United States and Qatar. This isn't just China's problem. It is a problem for every major chip maker, from TSMC to Samsung to Intel. They all draw from the same global supply chain. They all fight for the same shipments. But China is now trying to build an entirely domestic EUV ecosystem while depending on a material it largely does not control. They have to find new ways to recycle it, capture it, and reuse it, because every drop counts. Because of this, Beijing reportedly put an emergency ban on all helium exports. They are hoarding every molecule they have for their chip factories. The deeper you look into this machine, the more you realize it isn't just limited by giant inventions. It is limited by thousands of invisible dependencies. Some are billion-dollar mirrors, some are decades of optical knowledge, and some are just a colorless gas that almost nobody thinks about. The helium problem shows just how deep the challenge goes. You can build the lasers and polish the mirrors, but if you can't keep the machine cool and leak-free, it won't run. Securing the gas is a massive logistical mountain to climb. But there is another resource that is even harder to secure than helium. You can't buy it, and you can't mine it. It lives inside the minds of the people who know how to make the machine work. The knowledge inside heads. When you look at all the physical parts of an EUV machine, it is easy to forget the most important part, the people who know how to make it all work together. There is one thing that sanctions and restrictions could never stop, and that is knowledge. You can block machines and components, but you can't block what is already inside someone's head. That may have been ASML's greatest advantage all along. They had decades of experience, trial and error, and a team of engineers who understood every tiny quirk of the machine. China didn't just need labs and research institutes, they needed experience. So they started investing heavily in bringing experienced talent back home. Some of the best Chinese engineers working overseas were recruited to return and join what became one of the country's highest priority technology programs. They offered huge incentives, massive labs, and the chance to work on a project that could change the country's future. It wasn't just a job, it was a mission. One of the best-known examples is an engineer named Lin Nan. He spent years working at ASML, specifically on the EUV light source. That is arguably the most challenging subsystem in the entire machine. After returning to China, he joined the Shanghai Institute for Optics and Fine Mechanics. There, his team rapidly began publishing research and filing patents related to EUV light generation. They took the knowledge they had gained and applied it to China's own unique approach. And China is investing so much money and putting so many smart people into the project that the effort is starting to show real results. When you look at research publications on EUV lithography, a very clear pattern emerges. For years, China published relatively little on the topic. Then, around 2020, the research suddenly takes off. Dozens of different teams started attacking different parts of the problem in parallel. Some focused on the lasers, some on the mirrors, and some on the control systems. This parallel approach is exactly how you solve a massive engineering problem quickly. Instead of one team trying to build the whole machine, you have 20 teams each solving one piece of the puzzle. Then, they slowly start putting the pieces together. The knowledge base grew incredibly fast. Every year, the number of patents filed in China related to EUV technology grows larger. It is a flood of new ideas, new materials, and new methods. This return of talent gave China a massive jumpstart. They didn't have to invent the wheel, they just had to learn how to build it themselves, using the experience of people who had already done it. The prototypes they are building today are a direct result of that returning knowledge. But knowledge alone isn't enough to run a factory. You need to turn that knowledge into hardware that works day in and day out. The report suggests that China now has a working EUV prototype. It currently delivers around 100 watts of power. That is a huge jump from nothing, but it is still behind ASML. ASML's production systems deliver roughly 300 watts, and some of their newest prototypes reach over 700 watts. There is still a substantial gap in power and efficiency, but China is closing that gap faster than anyone thought possible, because they have the people and the focus to do it. They have built the light, the mirrors, and the team. They are pushing the limits of what their engineers can do. But does China actually need to match ASML to win? The answer to that question changes everything about this story. The road to the factory. So where does all this leave us? China has a working prototype, but it only outputs about 100 watts, while ASML is pushing 700 watts. That is a massive gap. You might think that if China can't match ASML, the project is a failure. But that is not how this works. China doesn't need to build the world's best EUV machine. They only need to build a machine that is better than their current alternative. Right now, the Chinese chip maker SMIC manufactures its most advanced chips using a process called quadruple patterning DUV. This uses an older type of lithography machine. Because the older light has a longer wavelength, they have to pass the same silicon wafer through the machine 4 different times to get the tiny features they need. It works, but it is incredibly painful. Every time you pass the wafer through, you risk misalignment. The yields fall below 50%, meaning more than half the chips are broken and thrown away. Time and costs rise dramatically. And eventually, the physics stops you. You simply cannot keep shrinking transistors that way forever. You will never reach a 5-nanometer class chip using DUV. This means a domestic EUV machine doesn't have to beat ASML. It just has to beat quadruple patterning DUV. Even if the Chinese EUV machine prints fewer wafers per hour, even if it is not commercially competitive, and even if its yields are far below ASML's, it is still a huge win. If it can replace the 4-step DUV process with a 1-step EUV process, it changes everything for China's semiconductor industry. Remember, ASML needed about 12 years to go from its first working EUV prototype to a reliable commercial product. China will almost certainly need time as well. They have to scale up the power, improve the mirror lifespans, and secure the helium supply. But unlike ASML, this isn't just a commercial project for China. It is a strategic one. The objective isn't necessarily to build the most profitable machine. The goal is to build one that China completely controls. And then comes the final part, the part no one can shortcut. They have to turn a working prototype into a factory. The distance between "it worked one time in a lab" and "it runs 24 hours a day," printing hundreds of wafers every hour for years, is enormous. A prototype is fragile. A factory machine has to be bulletproof. It has to handle constant use, broken parts, and constant maintenance, all while keeping the tiny circuits perfect. To do that, they will need an entire ecosystem of support. They need technicians who know how to fix the lasers, software engineers who can calibrate the mirrors, and a steady supply of replacement parts. When an ASML machine breaks, they have a global network of engineers ready to fly in and fix it. China will have to build that entire support network from scratch. That is the road ahead. China has built what ASML feared most, a domestic EUV machine that doesn't rely on the outside world. They solved the light with giant spinning disks, solved the mirrors with massive scale, and brought home the brains to make it work. Now, they just have to make it survive the factory floor. The machine that takes up an entire factory floor is just the beginning. The true test will be how fast they can shrink it, speed it up, and turn it into the workhorse that builds the future of technology. They have crossed the starting line, but the marathon is just getting started. The stakes are incredibly high. If they succeed, the entire global chip industry will shift. If they fail, they will have spent billions on a machine that never leaves the lab. If you enjoyed this story and want to see more like it, hit the like button, subscribe, and turn on notifications so you never miss the next one. There are related videos on the screen right now if you want to keep watching. So here is a question for you. If you were building a machine this complex, which part would you try to build first? The lasers, the mirrors, or the software? Let me know in the comments.